We're going to begin our exploration of forces. And to do that, we have to talk about a few concepts first. So first, we're going to discuss something called Newton's first law. And what Newton's first law tells us is that an object will either stay at rest or it will continue along the straight path unless it's acted upon in some way. What do I mean by that? So we have a person just standing on Earth, and they'll basically just stay at rest until something happens. That makes sense. Like if you're just sitting down and you're not moving, well, you'll stay that way until either you get up and you start walking or something bumps into you. So that piece kind of makes sense. So that's when something remains at rest. The other idea that's a little different but still involves the same principles is, say, for example, you take a rocket ship and you're flying off into space, and when you first launch, there's a really great acceleration that's causing you to move. And you continue to move until you turn off your engines. And when you turn off your engines, you might be going at some very high velocity. It's going to be a crazy fast velocity. Let's say 1,000 kilometers per second. This is not meters per second. This is 1,000 times 1,000 meters per second. So you're going very fast. Well, Newton's first law says that you'll continue moving in a straight line at that same speed unless something happens. So you'd have to either get bumped into, maybe you hit an asteroid, or you could turn your engines back on. But otherwise, if you're in space, you will continue moving at this same speed. There's no friction due to air. Nothing is happening to you. It's basically just like you're standing still, but you could have some large velocity. So these are the two cases of Newton's first law, and they're kind of like our starting point for our introduction to forces. So we need to discuss another idea, and this is the idea of inertia. And an inertia is a resistance to a change in motion. And think about it. What is a change in motion? Well, acceleration is a change in velocity over change in time. So if you have some change in motion, you're going to be accelerating. And inertia is basically related to the mass of an object. So, for example, if a person would have some mass, m, let's call it mass m, and it doesn't matter where they are, whether they're on Earth or whether they're on Jupiter, the mass would be the same. The mass is actually a count of the amount of matter in your body. So the amount of atoms that you have comprise your body is the mass. This is different than the weight. We know, we have probably been told before that on Earth and Jupiter you have different weights. And that's because the weight is dependent on the force of gravity, or the acceleration that's caused by gravity. So we know on Earth it's little g equals 9.81. On Jupiter, this would be much larger, and we could call it capital G because it's larger. So the mass is independent of the weight. The mass is just a measure of the amount of atoms that are in an object, and the mass helps us determine the inertia. And we can actually graph the relationship between the acceleration and the mass on a chart. So the relationship is, for your acceleration, it's proportional to, that's what this little symbol that kind of looks like a fish, is proportional to 1 divided by the mass. So let's look at this. When the mass is very small, what is this value right here? Well, I can choose an arbitrarily small mass, as many zeros as I wanted. And if I choose this number that's very small, well, 1 divided by a very small number is a large number. So the mass begins up here. It begins when the acceleration is very large, because if I have a small mass, then I'm going to have a large acceleration. Hopefully that makes sense to you. Let's show an example. Okay, if I have a little sports car, we know that that has less mass, for example, than a large freight train. So if this is mass M, but I have a freight train that is many cars long, sometimes, I mean, they go for kilometers, depending on where you see one. They can be very, very, very long. Well, the freight train's going to have a lot of cars. It's going to have a lot of mass. So it's going to be more difficult to accelerate. It takes a long time for the freight train to get up to speed. We could say each one of these cars is little m. Well, this has 4 times m. That's much more mass than this small sports car. So it's going to be harder to accelerate. So as I increase the mass, well, then what happens? So the mass begins to increase, and you can start putting a larger number here into the mass, into this proportionality. And you could say m equals, you could say m equals 1,000,000. Well, then 1 divided by 1,000,000 is much smaller than 1 divided by a small number. So as the mass increases, it becomes more difficult to accelerate that object. And so the line begins to now move towards a equals 0. Well, that's kind of interesting, but it should make sense. So as the mass is small, down here is small, the acceleration is large. As the mass is large, well, then the acceleration is small. Again, this is the acceleration line right here. It's like a y value. It's like the vertical value. Okay, so as mass gets bigger, acceleration gets smaller. As mass gets smaller, acceleration gets bigger. That's what we mean by this 1/, relationship, this inverse proportionality. Okay, so hopefully that makes sense to you. This sports car is going to be accelerated much more easily than this large freight train. The sports car has less inertia than this large freight train. And the other idea then is that Newton's first law, so we have to keep this in mind. If you're at rest, you're going to remain at rest unless something acts upon you. Either you start walking or something bumps into you. And if you're moving with some velocity with no other bodies or forces acting on you, then you're going to remain moving in that straight line. In space, there's no friction from air, so once you reach your top speed, whatever that might be, you can cut off your engines and you're just going to remain at that speed. It's kind of like if there were no friction and you were driving your car at 60 miles an hour, if there were no friction and you just stopped your engine but let your car roll in neutral, it would continue rolling at that same speed if there were no friction. So these are some of the basic ideas. In the next video, we're going to get into the actual definition of force itself.